Hi, Chad. I was hoping you could introduce yourself and give us a bit of an intro into what we'll be discussing.
Yeah, certainly. Thanks for having me. So I'm Chad Pozarycki. I was recently at Georgia Tech doing a PhD in analytical chemistry, and most of what I've worked on for the past 6 or so years has been astrobiology related analytical chemistry. And so what that means is looking at samples that are relevant to detecting signs of life elsewhere in the solar system and on planetary science missions, and then also in environments here on Earth. So that's what I've been working on.
Very cool. So, this will actually be the second podcast that I've recorded that has had a space theme.
Oh, cool.
That other interview didn't involve chromatography mass spec,
Mm,
but students from a community college
mm.
sending a experiment up to the International Space Station.
Oh, awesome.
So yeah,
Nice.
that was focused on radish growth. That was a great interview. So obviously there's a lot of analytical challenges, and one thing that was specific to your paper focused on the high salt concentrations. Could you talk about
Yeah.
that?
Yeah, certainly. So the thing with planetary samples, and in particular, when I think planetary bodies, I've worked with Mars and Europa, and these planetary bodies have a lot of salts on their surface, just like Earth does. And so when you're looking at the organic compounds on the surface of one of these planetary bodies, what you want to do is pick up a sample from the surface and be able to analyze it no matter what that sample is. So if it includes a lot of salt, you have to deal with it. And so that's usually why salt comes into the picture. But just for an example, the Viking landers, they don't rove around, they were just planted on the surface. When they landed on Mars in the 70s, they didn't have a lot of choice of what samples to pick up, and they also didn't know exactly the composition of the regolith. And there was a lot of chemicals in there which affected the chromatography. And so that's something that we've had to deal with for, at this point, 50 years in planetary science.
What mass spectrometry detection methods did you employ in identifying and quantifying the biomolecules? And what was it, LCMS?
Sometimes people in astrobiology and in extraterrestrial material analysis use LCMS. At my work previously, so not related to the paper that I sent you, but related to some of the work I did previously at NASA Goddard, when we work with meteorites, we do use LCMS. We use a lot of preparatory procedures that involve desalting steps and derivatization steps to tag, say, amino acids, and then we'll put those into an LCMS. For this work, I use something called capillary electrophoresis. So it's another liquid-based separation technology, except instead of using a high-pressure liquid and using a stationary phase like you would in a liquid chromatography column, you basically have a charged layer on the surface of a really thin capillary, almost like a GC capillary, a fused silica. And by using the properties that are on the internal surface of that capillary, and then the electroosmotic flow, as we call it, so the electrical properties that are present inside of the capillary when you put a potential across it, that helps you separate the compounds based on their size and on their charge. So just like liquid chromatography or gas chromatography, it's a hyphenated method. So capillary electrophoresis can be put in front of a mass spectrometry system or also a laser-induced fluorescence system, for instance, which is another detector that I've worked on in that work.
And as a follow up, what ionization techniques prove most effective?
Yeah, so it's a good question what is most effective. When it comes to capillary electrophoresis mass spectrometry, I was using a system by 908 Devices called the Zip chip, and it's basically a glass capillary electrophoresis microchip that interfaces via nano ESI to, I used an Orbitrap for that analysis. And so ESI, obviously, ion suppression is a big issue there, and you want that cone, that nanospray cone, to really come out well. And so something that didn't work was when you have a lot of salts building up in that microchip, at the tip, you get a lot of crystallization happening as those salty, those brines are being ejected and sent to the mass spectrometer. I've also used GCMS for some analysis of other salty samples. And when you're doing pyrolysis, for instance, to volatilize that, it sort of prevents a lot of the really bad stuff from getting all the way to the mass spec, and also because it gets stuck in the GC's stationary phase. And so electron ionization or electron impact, that seems to be a little bit more robust, but that might just be because of the separation that's happening before kind of catching that. So yeah, and then the benefit, and so this isn't really ionization, of course, but the benefit of laser-induced fluorescence is you don't need to remove it from the capillary or change its state in order to detect the sample. All you need to do is, in our case, we derivatize with a fluorescent tag to amino acids. And so if you don't need to do ionization, then you don't deal with ion suppression. And so that's why we do laser-induced fluorescence for some of our analyses.
You're dealing with a lot of what I think is fair to call extreme environments. So
Yeah.
that must make it challenging in terms of validating the analytical methods. I was hoping you could talk about the key performance parameters you were looking for.
Yeah. So usually we design a method that works with just a standard of amino acids, and we get our analytical figures of merit, like you want good peak resolution. We calculate the theoretical plates. In that work, we flesh out what is the limit of detection under the best circumstances and limits of quantitation and the sensitivity and the signal to noise. But then when we add the salty samples for the method paper, this was like a capstone that we would add is we would take 4 molar magnesium chloride sample that we collected from one of our field sites. We would inject it just as we would a standard. In the case of capillary electrophoresis paired with laser-induced fluorescence, it actually fared really well. We didn't see any changes in those analytical figures of merit. When you do something with, say, mass spectrometry, you have definitely ion suppression. You have the peaks sort of building up, and then you also have a big salt front. As the amino acids are coming out, they sort of get pushed and stacked on top of each other by that salt front. The separation isn't as effective anymore. The resolution on the mass spec analysis that we did, which was paired with the microchip, wasn't as effective. Whether we actually put numbers down and said, okay, this salt is causing exactly this reduction in analytical performance, we actually didn't do direct comparisons. We didn't measure like, okay, did the LOD change from this to this? Um, but I think there's a lot of potential for work exactly like that in the field. One weakness I see in the field of environmental sample analysis and extreme sample analysis, like salty samples, is often you go to a field site, you analyze that field sample, and then you have the information for that field sample. But more rarely do you ever see that people take a method that's already in use and then the new method that they want to use and then a field sample and then perform sort of the analytical validation. So that's something that I think there's a lot of room for and that I would encourage new researchers or grad students to work on because it's something that, when you're dealing with a grant that is aimed mostly at getting scientific information about the samples, uh, you're putting more focus on trying to learn about the samples than you are learning about the analytical method.
Fair enough.
Yeah.
You're dealing with limited sample volumes and potentially low power. How are
Yeah.
the approaches adapted for, let's call it space based instrumentation?
Yeah, so that's a really good point. And just to make this idea clear to everyone listening, you have analog sample analyses that happen on Earth, and then you have the actual extraterrestrial sample analyses that happen in space. And so on Earth, what we're doing is we're going out into environments like, say, Western Australia, or some people go to places like Antarctica, where you have really dry samples, or the Atacama Desert. And they collect these and they either bring them back to the lab and they analyze them with a full size benchtop instrument, the kind that you would see in any normal analytical lab, or they'll analyze them there using something that's more portable and more like what you would see on a space flight. And so then on the other side, in spaceflight, of course, you need to automate that sample collection. You need to automate the processing of those samples. So you can't have someone there with a pipetter that's doing an extraction. Everything needs to happen inside of either the rover or the lander or whatever system is there. And so when it comes to power and size and mass, the big things that are really difficult to handle are, say you're doing pyrolysis. If you want to do pyrolysis at a really high temperature and you want that temperature to happen really quickly, you might be limited, for instance, by the rover's capability to provide that power. So the Curiosity rover has a slower pyrolysis ramp rate than you might usually use in an organic geochemistry experiment. And so that's one reason that we might not be getting as good of a yield as we would if we were using a faster ramp rate system. And then regarding mass and size, it's really just hard to put a lot of actuating and I guess manipulating systems inside of a spacecraft. And also, it needs to be able to survive the journey through space. It needs to survive the vibration of launch and of landing. And it needs to be really, really robust. And it needs to, not cause any, significant contamination issues. So if you're using derivatization agents, it's possible that those could in the end actually contaminate your system if anything went wrong.
Work with the tools you have available. It's part of the mantra, I suppose.
Exactly.
What recommendations would you give to other analytical chemists working on biosignature detection and challenging environmental matrices?
Yeah. So I think the thing that I learned later in the game that I wish I had learned earlier is that it's easy to get, really challenging, well, maybe not easy, but, there's a bunch of really challenging samples out there, and they're all going to challenge your analytical method in different ways. And most of the fieldwork missions are to get information about that field site. And if you're developing an instrument and you're funded to develop that instrument specifically, it's a little bit different. And you're really focusing on just how those figures of merit change based on the system that you're using. I think what I would recommend is to know exactly what the goal is for that project. And despite that, try to play both sides because you can't have analytical understanding of how things affect your method if you don't know exactly what's in the sample and why the sample is affecting your instrument. And then if you don't, the other side of things, it's sort of a two-way street. You need to know both what's the underlying geochemistry of the sample and the reaction of that instrument. And you can't draw conclusions about one or the other without both. So, for instance, in my thesis, we were trying to understand ATP in one of our ATP assays that we were performing was difficult to detect because there wasn't any there, or whether it was difficult to detect because there was a lot of salt and that was affecting the protein that caused the assay to work. And so it's all about deconvolving analytical effects from biological or geochemical effects. Again, just to summarize, if I could recommend anything to anyone going into analytical chemistry for environmental sampling or astrobiology samples, just really make sure you're looking at both the analytical effects and the environmental biological effects at the same time and separating them and trying to understand them individually.
For my next question, I'm not asking you to know the future by any means, but just based on your experience and trying to look forward to the future, what do you see for miniaturized chromatography, mass spec, and how that relates
Yeah.
to astrobiology research?
Yeah, so I think over the past 2 decades, we have really seen gas chromatography mass spectrometry be the dominant spaceflight instrument when it comes to separatory analytical chemistry. What I'd really like to see is a shift towards other types, particularly capillary electrophoresis, and also some maybe non-separatory methods, things that are direct injection, high resolution mass spectrometry. And so there's a lot of groups out there that are really focusing on both diversifying the separations, and then there are a few groups that are really focusing on improving the resolution of the mass spectrometer. I think that the next missions that go out to places like Enceladus are really going to have much more powerful mass spectrometers. I hope someday to see an Orbitrap out there. And then I think we're really going to need to have separatory systems that are redundant and that are liquid based. Because if we're going to ocean worlds, for instance, like Europa or Enceladus, it's going to make a lot more sense to use liquid systems like capillary electrophoresis. People have spoken about putting them to space flight. There's a couple abstracts from a decade or two ago, but I don't see many people pursuing LC in space because of the issues with solvent usage and how high volume those solvents are, how much they weigh. I think whether it ends up going capillary electrophoresis or whether it ends up going just, other method, the most important thing is higher mass resolution and understanding those analytical impacts of the sample that you're collecting. So if there's salts in your sample, or if your sample has a number of other different pH changes that you didn't expect, I think that's an important aspect.
What else do you think is important to tell the audience about this work?
Yeah, so I think right now astrobiology is sort of in this precarious state where the Mars sample return missions are a lot of people in my field are very much looking forward to getting samples back from Mars so we can do really advanced analytical science on them on Earth. Then getting funding for more missions out in space is also something that's been really challenging lately. And so what I would recommend for people that are interested in analytical chemistry regarding spaceflight is to just get really good at analytical chemistry, get really good at environmental chemistry, and when the time comes to put your efforts and your expertise towards these missions, you'll have the skill set in a more diversified way outside of just the narrow field of astrobiology. Learning other methods, even if you don't think that they're going to end up flying in space, or learning methods that you don't think are necessarily immediately compatible with field analyses, are still going to be really valuable for you to understand, because analytical chemistry at the end of the day is all about how to approach a sample and really get the most unbiased information out of it as you can, knowing the question that you have in mind. So I guess that's more of career advice. And then when it comes to actual analytical chemistry, when you're out there doing sample analysis, either in the lab or in the field, standard addition is probably the best friend that you can ever have. If you want to understand what the sample's doing to your system and also get a really good quantitative look what the composition of the sample is, doing standard addition, I mean, it's sort of like the basic bread and butter, but people often forget, people will do a calibration curve and then they'll run their samples afterwards. Standard addition is another way to approach it that I think is really, really effective when you have really challenging samples. So just keep that in mind, everyone, that it's a really powerful tool.
Yeah, that's great advice. Thanks for
Yeah.
sharing all this with our audience.
Thanks for your time. I'm glad to be here.